Lesson 11.5 is partial fraction decomposition. Partial fraction decomposition is writing a rational expression as a sum of simpler rational expressions, essentially working backwards from simplification. The way that we do that is we start with whatever our rational expression is and we factor the denominator completely. Each factor in the denominator gets its own denominator rational expression, and then we have to find our missing numerators using systems of equations. So essentially what we've always done is we've always started with 3 over x plus 4 plus 2 over x minus 3 and worked this direction to simplify it into one rational expression, 5x minus 1 over x squared plus x minus 12. Now with partial fraction decomposition, we're going to start with the 5x minus 1 over x squared plus x minus 12 and work backwards, factoring the denominator. Each factor of the denominator gets its own denominator, and then we're going to use systems of equations to figure out what these numerators are. So we're going to go from this one and work backwards to find the sum of rational expressions. There are two cases that we're going to be looking at when we do these partial fraction decompositions. The first case is if you have non-repeated linear factors in the denominator. So if we look at this rational expression, 3x over x squared plus x minus 2, the very first thing you always do for these is factor the denominator completely. You want to leave the numerators non-factored, but the denominators need to be completely factored as far as they can go. So x squared plus x minus 2 factors into x plus 2 times x minus 1. So these are non-repeated linear factors. Both of them are linear, and each one is unique. So now each of these is going to get its own denominator, its own fraction. So since I have two unique denominators, I'm going to have two fractions as part of my sum and difference of fractions. So x plus 2 is going to get 1, and x minus 1 is going to get 1. We don't know what the numerators are going to be, so we're going to leave them as variables that I'm going to call capital A and capital B. If I had a third one, I would call it capital C. Because the denominators are linear factors, the numerator is always 1 degree less, so it's going to be a constant term. So there are always going to be constants on these ones. Now what we're going to do is we're going to essentially work backwards. We're going to say we want to add these together, and so we need to make a common denominator and go the other direction. So I gave the x plus 2 the a and x minus 1 over x minus 1, and I gave the b the x minus 1 and x plus 2 over x plus 2 to make our common denominator to kind of work backwards again. So I end up with something like this. So since I know that these two are equal based on the way that I did this, I made this be equal to this, and then therefore this is equal to this. I know that this original one has to be equal to the new one that we have. So this one, this numerator here, has to be equal here because our denominators are equal. So we're going to use that to help us figure out what a and b are. So because these are all equivalent to each other, these denominators are already equivalent to each other, we know that our numerators, 3x, and a times x minus 1 plus b times x plus 2, they have to be equal to each other. So we're going to use that rule to help us figure out what a and b are. So I just distributed my a in here, so I got ax minus a, and I distributed my b, so I got bx plus 2b, and that has to be equal to my original numerator. I want every power of x that's on my left to have a matching power of x from my original numerator. So I have originally, my highest power is just a power of x, which I have in the original numerator, but I also have constants in my new numerator. So that means I need to have a constant in my original numerator, and I don't. So I'm going to have a plus 0 placeholder. Now, every power of x is going to be an equation. So I started with my powers of just power 1x. So I have ax plus bx. When I combine those like terms on the left, I know it has to simplify down to 3x. So ax plus bx has to be equal to 3x, which means if I take my x's out, when I just add the coefficients, a plus b has to be equal to 3. Now if I look at my constant terms, on the left I have negative a plus 2b. When I add those together, they have to cancel out because the original numerator didn't have any constant terms. So that means that negative a plus 2b has to be equal to 0. So now I have two equations with two unknowns, and I can solve this system for a and b. I used elimination method because I can just add these two equations together and the a's would cancel out. And so I end up with 3b is equal to 3 when I add these two equations together, which means b is equal to 1. And then if I plug that back in over here, I end up with a to be equal to 2. So I use this system of equations to figure out what a and b is. And then I always want to write my answer in context, which in this case is the actual partial fraction decomposition, making sure that I put a over the x plus 2 and put b over the x minus 1. So my final answer is 2 over x plus 2 plus 1 over x minus 1. If you had switched the order that you had written these denominators originally, your a and b numbers would be switched, but your final answer, what was over the x plus 2 and what was over the x minus 1, would still be the same. Here's another one, 5x over x squared minus 5x plus 6. Start by factoring your denominators completely and giving each unique denominator its own fraction, and then working backwards to find the new numerators. So go ahead and pause the video and find the partial fraction decomposition for this one. I started by factoring the denominator completely, so x squared minus 5x plus 6 factors into x minus 2 times x minus 3, which are unique non-repeated linear factors. So I gave each one its own denominator, so x minus 2 and x minus 3. These are both linear factors, so the numerators are always 1 degree less, so they're just constants a and b. Now going the other direction, putting it back together, I need to make a common denominator. So the x minus 2 needed the x minus 3 over x minus 3, and the x minus 3 needed the x minus 2 over x minus 2. So I end up with a times x minus 3 plus b times x minus 2 over x minus 2 times x minus 3. And since I know these are equal to each other and my denominators are already equal to each other, that means I know my numerators have to be equal to each other. So I distributed the a and b. I got ax minus 3a plus bx minus 2b is equal to 5x plus 0 because I need a constant term on the left, which means I need that missing constant term on the right. And then each power of x became its own equation. So I have ax plus bx is equal to 5x, which means a plus b must be equal to 5. Negative 3a minus 2b has to be equal to 0 because those are your constants, and so that became my second equation. Now I have a system of two equations with two variables, and I solved this system using elimination. I multiplied a plus b equals 5 by 2, added it, and my b's canceled. I got negative a is equal to 10, which means a was equal to negative 10. And then I plugged that in over here, and I got negative 10 plus b is equal to 5, which means b was equal to 15. So then my partial fraction decomposition is negative 10 over x minus 2 plus 15 over x minus 3. The second case we're going to look at is if you have repeated linear factors, which means you have a linear factor like x minus a, and it's raised to a power. So examples of that, this is already factored completely. So x is a linear factor, and it's been raised to the power of 2. X minus 2 is a linear factor, and it's also been raised to the power of 2. So similar, each denominator gets its own fraction denominator, but we also have to include every possible power of x. So if I have an x squared, I have to have an x and an x squared. If I have an x minus 2 squared, I have to have an x minus 2 and an x minus 2 squared. If it was x minus 2 cubed, I would have to have x minus 2, x minus 2 squared, x minus 2 cubed, all the way up to whatever power is shown. So for this one, it's already factored completely, so my x squared is going to give me an x and an x squared. My x minus 2 squared is going to give me an x minus 2 and an x minus 2 quantity squared. Each of these is linear. Even though these ones are squared, they're originally linear factors. They've just been raised to a power. So all of my numerators are still going to be constant. So I have a, b, c, and d. Sometimes some of the numerators will cancel out. You'll get like c equals 0. But we always have to assume that we have all of them, and then if some cancel, they cancel later. Now it's the same as the previous one. I want to work backwards so that I can get this common denominator. So I have to think about what each of these is missing in order to make this common denominator. So for example, the first one has an x, which means it needs one more x to make it x squared, and it needs the x minus 2 quantity squared. The b already has the whole x squared, so it just needs the x minus 2 squared. The c has one of the x minus 2, so it needs one more x minus 2 and the whole x squared. And then the d has the whole x minus 2 squared, so it just needs the x squared. So then I'm just writing out the numerators because the denominators are going to be the same and I don't want to get confused with more letters. So this is what my new numerator is going to look like. So my new numerator has to be equal to my original numerator. So I'm going to FOIL all this out and then set it equal to the x plus 1, where I have every power of x on the left has a matching power of x on the right. So when I multiply everything out, x minus 2 quantity squared is x squared minus 4x plus 4 times ax is going to give me ax cubed minus 4ax squared plus 4ax. And then that thing times b is going to give me bx squared minus 4bx plus 4b. Cx squared times x minus 2 is going to give me cx cubed minus 2x squared. And then dx squared is just dx squared. So on the left, I have powers of x at cubed, squared, linear, and constant. So on the right, I need to have the same thing. My original numerator doesn't have a cubed or a squared, so I'm going to have a 0x cubed and a 0x squared to have as my placeholders to match with my left, and then plus the x plus 1. So now same idea as previously, it's just going to be more complex because now I have 4 terms that I need to write, which means I'm going to have 4 equations. For my cubic, I have ax cubed plus cx cubed, and that has to be equal to 0x cubed. So that means that a plus c has to be equal to 0. For my squared, I have negative 4ax squared plus bx squared minus 2cx squared plus dx squared, and that has to be equal to 0x squared. So negative 4a plus b minus 2c plus d equals 0. For my linear, 4ax minus 4bx has to be equal to 1x. So 4a minus 4b has to be equal to 1. And then for my constants, 4b has to be equal to 1. So 4b equals 1. So now I have 4 equations with 4 unknowns. Sometimes this can get very complex, but a lot of times it's kind of a rainfall. So I can start finding one, for example, the b, plug that in, find the next one, plug it in, find the next one, plug everything in, find the 4th one. I started solving this by first solving for the first one, b is equal to 1/4, because I had 4b equals 1. And then I plugged that into the 4a minus 4b equals 1 and got a to be 1/2, which I then plugged into the a plus c is equal to 0 and got c to be negative 1/2. And I plugged all of those into negative 4a plus b minus 2c plus d is equal to 0, and then solved for d, and so I got d is equal to 3/4. So even though there was 4 variables and 4 equations, it was pretty easy to solve by substitution just because the first one was easy and then you moved on, so on and so forth. And then again, the last step is making sure you write your final answer in the actual partial fraction decomposition. So plugging each one in, I get 1/2 over x plus 1/4 over x squared minus 1/2 over x minus 2 plus 3/4 over x minus 2 squared. So whenever you have the repeated linear factors, you have to have every power from 1 up to whatever 1 is shown. Sometimes one of the lower powers will cancel out, but you always have to assume that they're all there. Here we have another one, x cubed plus 1 over x to the 5th minus x to the 4th. So again, same thing, start with factoring the denominators completely, and then solve this partial fraction decomposition. Factoring this completely in the denominator, I factored out an x to the 4th, and I was left with x minus 1. So this is a repeated linear factor, which means I have to have every power from 1 up to what's shown. So I have x squared, x cubed, and x to the 4th. And then the x minus 1 is a non-repeated linear factor. So these cases aren't exclusive, they can be working together. So I also have an x minus 1. And then my numerators are a, b, c, d, and e. So I'm going to have 5 variables, which means I need 5 equations. So working backwards, the first one already has an x, which means it needs an x cubed and an x minus 1. The second one has an x squared, which means it needs an x squared and an x minus 1. C has an x cubed, which means it needs an x and an x minus 1. D has an x to the 4th, which means it just needs the x minus 1. And then E has the x minus 1, which means it just needs an x to the 4th. So then multiplying everything through, I end up with ax cubed minus ax to the 4th minus ax cubed plus bx cubed minus bx squared plus cx squared minus cx plus dx minus d plus e times x to the 4th. And then that's equal to the original numerator. I didn't have any originally x to the 4th, so 0x to the 4th plus x cubed plus 0x squared plus 0x plus 1. So then each power of x from 4, 3, 2, 1 constant is going to be its own equation. So starting with the 4's, a plus e is equal to 0. Negative a plus b is equal to 1 for the x cubes. For the squareds, negative b plus c is equal to 0. For the linears, negative c plus d is equal to 0. And then for the constants, negative d is equal to 1. So then that was a nice easy one to solve. I got d is equal to negative 1, which I plugged into the negative c plus d is equal to 0 and got c to be negative 1, which I plugged into the negative b plus c is equal to 0 and got b to be negative 1, which I plugged into the negative a plus b is equal to 1 and got a to be negative 2, which I plugged into the a plus e is equal to 0 and got e to be 2. So then my partial fraction decomposition is negative 2 over x minus 1 over x squared minus 1 over x cubed minus 1 over x to the 4th plus 2 over x minus 1. So for partial fraction decomposition, factor your denominator completely. Every unique factor gets its own denominator. Any powers, you start at 1 and have a denominator for every power up to whatever is shown. give them constant unknown numerators, and then work backwards, make your common denominator again, and set your new numerator equal to your original numerator, and every power of x becomes an equation that you can then solve a system of equations to find your variables.